by 12 plus by 159 over 145 times by 1.867 minus 1 close bracket squared. The whole thing is 1.1899 inch to power 4. Okay, so that's for the aluminum. Then we have the I of brass, right? So this is 1.51 cube over 12 plus by 1.5 multiplied by 1.867 minus by 2.5 squared. Okay. So 1.5 times 1 power 3 divided by 12 plus by 1.5 times by 1.867 minus 2.5 squared is equal to 0.726. So the IZZ we found is equal to 1.1899 plus by 0.726, right? So 1.1899 plus by 0.726, we got 1.9159 inches to power 4. Okay. So when we look at the solution manual, the answer is not the same. The answer is 5 point. So this is for aluminum, right? So for I, for ours is equal to 1.9159 inches to power 4 for steel, right? So if how can we compare these two numbers now? Okay, so if you look at the multiplier down here, right, it's 2.7358. So if you take 1.9159 multiplied by 2.7358, okay, so 1.9159 minus 2.7358, the answer is 5.2415 inches to power 4, which is the same, right? This is a reference material steel, this is aluminum. So to convert, you just put a multiplier, you just times the number is the same. So we are on the right path. Okay, can you see that? Okay. Any questions so far? Okay, so this is the way you should, if you want to use the solution manual, don't do exactly what they do, do something different, but make sure that your steps or your sequence of steps is similar to what I've taught you. Okay, right. But this is a good way to check. Okay, as I said, we pick different reference material, but in the end our answer should be the same. Okay, so now the question now asks, we are going to find A. Right, so let's see what we have. We know IZZ, we know VY, thickness we know, thickness all are constant is 1.5 inch, right? So the only one thing that changes is QZ is a variable for this case. Okay. So let's look at A. We're going to find the average stress. Okay, at the bonded surface. Okay. So if we were to construct our structure, okay, so this is our structure. So we have our steel, we have our aluminum, and we know that the centroid, right, from the bottom is 1.133. Okay, so I'm going to sketch out our centroid. Okay, so this is our centroid. and the distance from here to here is 1.133 inches. Okay. So they asked us to find what is the shearing stress on the bonded surface. So this line they've drawn down here, this is the bonded surface. So I'm going to call above the centroid as top, below the centroid as bottom. Okay. So I realized that the bonded surface is at the bottom. So we're going to analyze the bottom. Okay. So again, we're going to look at the 4 rules. Some of you will say, Eugene, can we do it from the top? My answer to you is no, based on these 4 rules. Okay. But the solution manual did it from the top. I don't want you to learn from there. Okay, because it can be really, really confusing for you guys. Okay. So, but our answer based on these rules, our answer should be the same. Okay, I will advise you to comply to these rules because I solve a lot of problems with these rules, and these rules make the solution procedure less confusing. Okay, so now you can see our rules. Okay, so we're going to analyze from the bottom, right? Why we analyze from bottom? Because the bonded surface is at the bottom. Okay, so we're going to find QZ is equal to A y bar. Okay. Now, because our reference material is steel, okay, we can just rely on steel. Okay. So so it's N, okay, width multiplied by depth multiplied by y bar. All right. So our N is 1, right? Width is 1.5. Our depth is 1 inch. Then the centroid is 1 point, or y bar is 1.133 minus by 1 divided by 2. Okay. So this will be equal to 1.133 minus 0.5 times 1 times 1.5 is equal to 0.9495 inches cube. Okay. So now we can find the shear stress of the bond. Okay. So Vy we know is 4 times 10 to the power 3. Your Q is 0.9495. Your I is equal to 1.9159. And the thickness is 1.5 inches. Okay. So this will work out to 4 power 3 times 5.9495 times 1.9159 divided by 1.5 is equal to 1.321. Okay. 1.322 in fact. 1.322, right, times 10 to the power 3 psi. Okay, so look at the solution, right? It's the same. Okay, you got 1.323. Ours is 1.322. Okay, our numbers are different, as you can see down here. Okay, our first moment of area is different because they took their first moment of area. They did not comply to our rules. This is the first moment of area they took. Okay, I don't want you all to follow that technique. Okay, don't. Okay, because later on, when we have more complex structure, you'll get confused. Okay, so don't follow. Don't. What I'm trying to say is, when you use a solution manual, check for key information like this. How you get there? Okay, use the technique that I teach you. Okay, don't try to figure out the solution manual. You get nowhere. Okay. Right. So the next part is B. Okay. So I'm see. Can I squeeze B here? No, I'm going to do on a new page. So I'll still put the rules. So B, you're going to find the maximum shearing stress at the centroid. Okay. Now, if our approach is sound, okay, we can analyze either from the top or from the bottom. The answer has to be the same. Okay, or not mathematically, our rules are flawed. Okay, so we're going to prove this concept. Okay, so we're going to analyze from the top. Okay, so determine tau max from the top. Okay, we're going to determine. Then I'm going to do side by side from the bottom. Okay, so from the top, right? So I'm going to sketch. Not sketch, but I'm going to copy this thing over. Right. So now you can see. So we also know the distance from here to here. We found this out, and it was 1.867. Okay. So we're going to deal from the top, right? So a Q Z from the top is equal to N A Y bar, right? So we have it as 53 or 145. The area is the width, 1.5, multiplied by the depth is 1.867 from the top, right? So from the top means we are analyzing at the aluminum section only. And Y bar is 1.867 divided by 2. Okay. So this is equal to 53 divided by 145 times 1.5 times 1.867 divided by 1.867 divided by times 53 over 145 times 1.5 times 1.867 times 1.867 divided by 2 is equal to 0.95, 0.9556, okay, inch to power Q. Okay, so I do it again, 33 over 145 times 1.5 times 1.867 squared divided by 2, 0.9556. Okay, now I'm going to do the same, but now determine tau max from the bottom. Okay, so the QZ from the top and the QZ from the bottom will be the same, right? Why is that? Why do I mention that? Because the shearing stress max is going to, we know that Vy over Izz are constant. T is also constant at what? 1.5. So the only thing that will change will be what? The QZ. The rest is all constant. Okay. So now I'm going to analyze. Okay, I'm going to analyze, right? Determine just side by side so you can see the difference. Okay. So we're going to determine tau max from the bottom. Okay, so we are going to, so the Q Z is equal to going to be the QZ of the steel plus by the QZ of the aluminum, right? Okay, so QZ